All right, 5.3. We're talking about one rule, basically. First thing you need to get in mind is this idea of independence. When are two events independent? And the answer is when the fact that one happened or didn't happen does not affect the probability of the other happening or not happening. Notice this is not disjoint, this is independence. Totally different thing. Let's play a little quiz here. Independent or not? And the first one is two rolls of a die. So I'm going to roll a die, and then I'm going to pick it up and roll it again. Just seeing if everybody's got the calculator.
Thank you.
You're welcome. Independent or not? Does the fact that the die came up 6 the first time affect the probability of what's going to come up the next time? Not at all. So those are independent events. Drawing two cards, and notice it says with replacement. So I'll draw a card, look at it, put it back in the deck, draw another card. First draw? What's the probability of getting a king? There's 4 of them in a deck of 52 cards. 4 out of 52. So that fraction. I put the king back in there and I draw another card. What's the probability of getting a king? Yeah, see, so those are independent events. Now contrast that with I draw a king out and I lay it on the desk and I now draw another card out. Independent? No. Now what's the probability of drawing a king? 3 out of 51. You all are right. See, the probability of getting a king changed once I knew I had drawn a king the first time. We're going to talk about that kind of thing tomorrow. So those would not be independent events. So when you're reading questions like this, always check to see if it's with replacement or without, because it affects things.
Wait, so with replacement is independent?
Yep. So our third one here, education past high school and earning at least $50,000 per year. Those are two events. Some education past high school and earning at least $50,000 per year. Independent or not? Now notice it says education. It doesn't say college. Could be college. Could be trade school.
Not?
Not independent?
I don't think it would be.
How come?
Because I don't know. I mean,
I'm
I'm
thinking
jobs,
in my head, but I don't think it's making sense.
and a lot of jobs get paid more the higher education you have.
Yeah, just think in general. In general, if you go to college, are you going to earn more money than if you just have a high school diploma? Yeah.
Whatever you're,
Yeah. So even 1 or 2 years of college, you tend to make more. You know, the more education you have. Whatever kind of education that is, could be on-the-job training. You could sort of apprentice yourself to a welder and learn how to weld. Well, that's education. They say if you really want to know how to do something, find somebody that knows how to do it really well and just tag along with them. Learn from them because they're already doing it right. Let's keep going. These two things are really confused a lot. Disjoint events and independent events. You're really going to have to watch yourself not to confuse these two. Disjoint events, they don't have any outcomes in common, or you could say it another way, they can't both happen at the same time. If I'm drawing one card from a deck, it can't be a king and queen. If I'm rolling one die, it can't be a 4 and a 5. Those would be disjoint events. But independent means something totally different. One event doesn't affect the probability of another. So if I say the probability of Peyton going to the office between period 2 and 3 is 0.1, and the probability of Haley going is 0.2, are those disjoint events? Yeah. They could happen at the same time. They could go down there together. So does that make them disjoint? No, they're not disjoint. They can happen at the same time. Are they independent? Yeah, probably. The fact that Peyton goes doesn't affect whether Haley goes or not. In general, right? So they're independent, but they're not disjoint. You got to get in your head, this disjoint means they can't happen at the same time. Let me ask you a question then. Let's pick another thing. Let's say that Evelyn we're having an election in the class. Let's say the probability that Evelyn wins is 0.5, and the probability that Parker wins is 0.4. Are those disjoint? Yes, they are. Both of them can't win. Why are they independent then? Bailey's saying no. How come, Bailey?
Because if Evelyn wins, then is it Peyton? Is that the other person?
Parker.
Parker. Then Parker does that, and Parker wins, then Evelyn does that.
Right. The fact that one of them happens, pick Evelyn. The fact that Evelyn wins made the probability that Parker can win 0. Yeah? Because they both can't win. If Parker wins, the probability that Evelyn can win is 0. The fact that one of them happens affects the probability of the other happening. With the Haley-Peyton thing, does the fact that Peyton goes down to the office affect whether Haley does or not? No. Okay, so either Kenna or Paige will get the last Oreo. Disjoint? Yeah. They both can't get the last Oreo. Independent? No. As soon as one of them has that Oreo in her hand, the other one can't have it. The fact that one happens greatly affects the probability of the other happening. You seen a pattern here? Here's a big idea. If two events are disjoint, they can't be independent. The fact that one happens or doesn't happen affects the probability of the second one happening or not happening. And to be independent, the fact that one happens doesn't affect the probability of the second. Getting these two things right is one of the really big sticking points for statistics each year. Knowing the difference between disjoint and independence, and knowing that if two events are disjoint, they can't be independent. I say that the only way that they could be independent is if one of them has a probability of 0 to start with. Doesn't happen very often. So for our purposes, just say, okay, if they're disjoint, they can't be independent. Can they? Let's look at something. Just talking about logic here. Okay, this is an if-then kind of thing. If it rains, then I'll take an umbrella. It's got two parts. Can I turn it around and say, if I take an umbrella, it will rain? No, see, I can't flip them. In general, there's some mathematical things you can. Could I say, so I can't just flip them around. Could I say, I won't take an umbrella, if it doesn't rain? Now look what I did. This doesn't have it. Well, it does have something to do with stats, but you won't be tested on this. But it's logic, and if you're taking SAT tests and all different kinds of tests, some of them have logic questions on them. If this is true, can you turn it around like this? Look what I did. I negated this, and I negated this. I can turn it around like this, and that's true. If the first one's true, so's the second one. If it's a dog, it's got 4 legs. If it's a dog, it's got 4 legs. Can I turn it around and say, if it's got 4 legs, it's a dog? Nope. Can I turn it around? And this thing right here is called the contrapositive, if you're ever interested in that. It's where you negate both of them. Positive. Can I turn around and say, if it doesn't have 4 legs, it's not a dog? I'm negating both of them. Yeah. See, so I can take the original thing, basically put not in front of each part and flip it, and it's okay. All right, anyway, getting back to what we were talking about. If they're disjoint, they are not independent. I can turn around and say, if they're independent, they are not disjoint. Because I knotted both of them, if you will. What I can't say is if they're not disjoint, are they independent? No, not necessarily. They might be. Is that confusing enough?
If they're independent, they cannot be disjoint.
Correct. Just a little logic thrown your way there. Okay, there's that thing we did. Here's a multiplication rule. Well, let's take it a chunk at a time here. This is version 1. I'll give you a chance to write it down, and then let's talk about it. It takes a keen eye to notice that I'm stressing if and independent here. It's a big if, literally, and independent is real important. So this is why you have to know what independent events are. If A and B are independent events, then I can get the probability of both of them happening by just multiplying their individual probabilities. That's a big deal. If we start off with independent events, and I want to know the probability of both, that's why that word and is in there, I can just multiply their probabilities. Tomorrow we're going to talk about what happens if they're not independent. That's going to be version 2 of this rule. We still just have 5 rules. Okay, we decided Haley going to the office and Peyton going to the office were independent. They weren't disjoint. They were independent. So what's the probability that both go? I'm trying to remember what I had on there. I think Haley, I think you might have been 0.1, and Peyton might have been 0.2. I don't know. We're going to go with that right there. What's the probability both of them go? That? Okay, they are independent. That way I can just multiply their individual probabilities. Notice something, y'all. This is real important. This is an and kind of thing. This is an and kind of thing. What was the addition rule? Or kind of thing. Thank you. If the problem's an and kind of thing, think multiplication rule. If it's an or kind of thing, think and or multiplication rule. So and goes with multiplication, or goes with addition. So what's the probability? Let's go back. That Haley or Peyton go. See if y'all can come up with that. Little trip down memory lane here. Is it an and or an or thing? It's an or thing. Okay. So we think addition rule. And we've got 2 flavors of that. Which one do I use? In this one little scenario, we could come up with a bunch of different kinds of questions. Anybody got an answer? Am I hearing 0.3? Anybody? 0.3? We good? We know they're independent, right? Are they disjoint? This is an or thing. Is it possible both of them could go? Yeah. So I've got to say the probability of the first plus the probability of the second minus the probability of both. Well, what's the probability of both? 0.02. Right? So it's going to be what, 0.28? 0.3 minus 0.02? 0.28? Just that one little switch can really mess you up. What's the probability neither goes? What's she saying, Peyton?
I don't know.
Okay, she waves it off.
Is it 1 minus the outcome of the second example? 0.1.
Is this an and thing or an or thing? Neither. Is it an and thing or an or thing? This will drive you all crazy. We only got 5 rules, and this is going to drive you nuts which one to use. If neither, doesn't it mean
What if we
not
use
her
both?
and not her?
What if we use both, but you subtract it, you do 1 minus both?
Yeah, wouldn't it be 1 minus 0.3?
Let's see. What's the probability that Haley won't?
0.9.
What's the probability Peyton won't?
0.8.
Now look at that. The probability that neither is an and kind of thing, but isn't it the complement of the either or thing? This will get you.
So,
Yes, sir.
So this is subtracting the numbers from 10 or
From 1.
0.9.
Yeah, if the probability of you going is 0.1, the probability of you not going is 0.9. And since it was an and thing, you're not going, and at the same time, Peyton's not going. Questions about that? You're going to have to play with this in your head. Okay, and I kind of messed up here. Let me erase some of this. Okay, I think I can read it with the blue on there. What's the probability of flipping a coin 4 times and getting heads each time? First of all, is this an and thing or an or thing? And, because it's heads and heads and heads and heads.
So is it like
Then the next question is,
5 times 0.25 times 0.25?
Or wouldn't it be 0.5?
what's the probability of getting heads?
Oh wait, not 0.25, 0.5.
Yeah. Are these independent? So we know it's an and thing. Are they independent?
Can you multiply it?
Is each flip of the coin independent of the other flips?
Yeah.
Yeah, because the fact that I got heads the first time doesn't affect the probability of getting heads the next time. So they're independent. So that means I can use this version 1 of the multiply rule. So the probability of all 4 is 1/2 times 1/2 times 1/2 times 1/2.
Yeah, that's what I meant.
I knew it was.
Yeah.
Now, what does this mean? It means that if I perform this flipping 4 coins things thousands of times, thousands and thousands and thousands of times, about 1/16 of the time, I'd get 4 heads in a row. I'd get all heads. Would that be the same as flipping 4 coins once? Yeah, because 1 coin is independent of the other coins. So I could either flip 1 coin 4 times or 4 coins 1 time. And getting all heads is still only going to happen 1/16 of the time. Does that make sense? So if I said, hey, Bailey, I'll bet you $1, I'll give you a coin, a silver dollar. I'm going to let you flip this silver dollar. It's worth a lot of money. If you get 4 heads in a row, you get to keep it. And if you don't get 4 heads in a row, you give me $1. Would you take that bet?
Sure. Nothing to lose.
Nothing to lose?
Well, then you have the
No, you've got a dollar bill.
Oh, I've got it?
I give you my lucky silver dollar to flip. Would you take that bet?
I guess not.
I think I've got a live one on the line here. After class, let's bet. How many times out of 16 are you going to win? One. Now, could you win? Sure. But I would expect you to lose 15 times out of 16. That's what that probability means. Let's pause for a second. A stats project? That would be neat. It would be neat for you all to find out how many other students in this school don't have a clue of how these numbers work. Because teachers included. Teachers included. No offense to anybody. It's just if you haven't looked at it, it's like, okay. Here's a strong hint. The probability of at least one, well, look at the first thing. At least one is the opposite of none. At least one means the opposite of none. Let me reiterate. At least one means the opposite of none. So, the probability of at least one is 1 minus the probability of none. Sort of a twist on the complement rule, isn't it? If I know the probability that none of these things are going to happen, the probability of at least one happening is 1 minus the probability of none of them happening. We said a minute ago the probability of Peyton or Haley going was what? 0.28? If I'm remembering right. So doesn't that mean at least one of them? If you think you got to really invest some thought in this. Peyton or Haley, doesn't that mean at least one? And we said the probability of neither was 0.72. That's this rule in action. If you know the probability that neither will go, the probability of at least one of them going is 1 minus that. And it looks so easy when you're taking notes on it and you think, oh, yeah. I got it. And then you get a word problem, which you're going to have in the homework, and you're going to go, how do I do this? What rule do I use? Here's a sample problem. Don't write this down. It's in the book. It appears to be problem 34 at the end of section 5.3. So read this. They're asking, we got two events, luggage check time and lost luggage. Those are the two events we're talking about. Are they independent? Brenda's saying yes. We got a super smart person saying yes, they're independent. Everybody? So we can just go on? Those are independent? Mr. Neal? Why aren't they? See, on a quiz it'd be, are these independent? Please explain.
They're not independent because it depends on what time she gets there.
What does?
I read that
The
wrong.
time that they get there prior to departure affects the percentage of getting lost.
Does the event luggage check time affect the probability of lost luggage?
Yes.
Yes.
I read that first as like the percentages. It said like luggage checked 1 hour and then luggage checked late. I don't know why.
It's just part of it really is part of the problem. First of all, most people are not used to doing word problems. It's like, find the vertex of this parabola. Okay, got it. But it's not used for anything. So we got two events, luggage check time and lost luggage. Does the check-in time affect the probability of the lost luggage? Yeah, it does. So they're not independent. Could I use the version 1 of the multiply rule? Nope. I could not. All right, let's look at another one. Gosh, this is fun. Christmas lights. Read this one, please. Okay, let's get some good thoughts here. Anybody got an idea about this one? What's the probability that in a string of 100 lights, all 100 last 2 years? First question, is it an and thing or an or thing?
And
How come?
because it's the first light and the second light.
Good. Good. It's the first one and the second one and the third one and the fourth one all the way up to the 100th one. So we know it's got to be a multiply rule. If they're independent, are they? Bailey says no. Katie?
I don't know.
Okay. Let's read the problem. Look at the problem. It says they are. So you're saying the problem's lying to you to confuse you. Man, I hate it when problems lie to me. These are independent because the problem told us that they were. All right? So it's an and thing. They're independent. I can use the multiply rule. So what do? I say the probability of 100 lasting equals
0.995 times itself like 100 times.
so 0.995. That's the probability of each one lasting raised to the 100th power. What do you get?
Oh, that's easy. Real quick. How is it independent?
It says if one bulb burns out, it doesn't affect the others.
This means that when one light burns out, the entire string of lights goes blank.
The success or failure of a bulb is independent of the success or failure of the other bulbs. Now, when one of them does go out, the whole thing's wiped out.
Right.
That's the confusing part. But whether bulb number 1 goes out or not doesn't affect whether bulb number 20 goes out or not.
Also, because if one goes out, then they all go out.
Yeah, we're just talking about, you have to take them individually. This one and this one and this one. I know they all go out when one does.
Mm-hmm.
Okay. Think about it.
I am thinking.
I know you are. I know you are. And I see how you could think that. And that's not unreasonable at all.
Are we gonna have some confusing question like this on
Oh, yeah.
and stuff?
That's why I'm wanting you to get used to it. So what do we get when we say 0.995 to the 100th power?
Or 0.6.
Point how much?
Are we rounding?
Let's go to 3 decimal places.
6.
Okay, so the probability that all 100 last is about 61%. So when you buy this string of bulbs, the probability that they'll all last 2 years is about 61%, a little less than 61%. Okay. Look at part B. What's the probability that at least one will? Oh, yikes. Will burn out.
At least. Oh,
Can I just say 1 minus 0.606? Is at least 1 the opposite of
Yeah.
all?
No, but what if you do 1 minus 0.606? Wait, what?
Wait, would it be 1 minus 0.995?
That's what it would be for 1.
Okay, so then.
So this bulb right here, the probability that it will burn out within 2 years is what? 0.005? Right? Because the probability it's going to last 2 years is 0.995. So the complement rule says, well, the probability of it not lasting 2 years is 1 minus 0.995.
So it would be 1 minus 0.606.
Let's see. Let's go back in the notes.
Yeah, that's what it says.
Let's go back in time. Oh, man, look at this.
Are you trying to confuse us for no reason?
No, the problem's doing that. And I'm saying, I'm not trying to be mean. I'm saying these will send you to the next room talking to yourself. We only have 5 rules. But trying to decide what to use is the hard part here. You know, most of us, when we think of probability, it's like, okay, I got 9 green marbles and 10 red ones. What's the probability of getting a green? Okay, good. But here's the kind of problems you're going to be faced with. This is more advanced. The probability of at least 1 is 1 minus the probability of none. Get that in your head. So we go back over here. So how am I going to get the probability of at least 1? Well, burning out. What do I need to know? All of them lasting 2 years? This is talking about burning out. So what do I need to know? The probability of what?
So would it be 0.005 to the 100th power?
How are you getting that?
Because the probability of it making 2 years is 0.995, so the probability of 1 not making it 2 years is 0.005, and then there's 100 options.
That would be the probability of all of them burning out. Wouldn't it?
Right.
I did that to the 100th power and I just got 0.
It's such a tiny number, the calculator goes to heck with it. You know, you're on your own.
Gotcha.
Even though it's not 0. Because the calculator's memory is finite. It can't keep track of all those digits.
So we got to get to none.
What's the probability of none of them burning out?
Probability of none of them
So the probability that none burn out
is,
how do I get that?
is that already 0.606?
Is that the same thing?
100 of them lasting?
That's the probability of none of them burning out.
Yeah, and then so 1 minus 0.606.
So,
So it's 0.3.
so we already had it. So the probability of at least 1 burning out is 1 minus 0.606.
So you just did that all to confuse us.
No, I want you to understand it.
I understand.
This is, okay, all right. You get the gold star for the day. So this is going to be what, 0.394? If the probability of none of them burning out is 0.606, the probability of at least 1 is 1 minus that. It's the same thing as the Haley and Peyton going to the office thing, just in more confusing terms. Let's look at another one. Yeah, if you want the probability of all of them burning out, it's a number so small that the calculator just goes, let's just call it 0 and be friends.
Not friends with that calculator.
We got Ralph at the bowling lanes here. So let's look at A. He gets a strike 30% of the time. So the probability of 1 strike is that.
Yeah.
Okay, A says, what's the probability he'll get 2 strikes in a row? Stop right there. Is it an and thing or an or thing?
And
And, because it's strike and another strike. So it's an and thing, so I'm thinking multiply rule. So the probability of strike. Oh, would they be independent of each other?
Yes.
You could argue that they would be. Although, if you've ever been bowling, you can go one time and you hit the gutter every time and your score is like 15. And then you go another time and you can't do anything wrong. And you roll 180 or something. So you could argue maybe not independent if you're having a hot streak. But let's just say they're independent. Okay, so that means I could multiply those two probabilities together, right? So point. And that's going to give me what? That? So less than 10% of the time, he's going to get 2 strikes in a row like that. All right, we look at part B. What's the probability he'll get a turkey? 3 strikes in a row. Still independent? Okay, so I can say raised to the 3rd power. And is that right? No, 1 less 0. I did that first period too. All right. So less than 3% of the time, he's going to get 3 strikes in a row. Now it says when events are independent, their complements are 2. So what's the probability he would get strike, miss? And thing or thing? You're right. You're right. Strike, and miss. So what can I do? Okay. Peyton's saying, we'll take this 0.027 because that's a probability of 3 in a row. So that would be this, right? 3 good ones. Times, what's the probability that he misses? Good. So I multiply those two things together, and what do I get? 0.7 times 0.027. Thank you. So if you're betting, he's going to get 3 strikes and then miss. That's the probability of that happening, less than 2% of the time. If you want to take a picture of that, you can. This is the kind of problems you're going to be faced with.
How did you know this percentage of missing?
Hmm?
How did you know this percentage of missing?
Say one more time.
How did you know this percentage of missing?
It says so. He gets a turkey and then misses on the 4th one. All right, let's look at, our defense system. So we have a satellite defense system that's got 4 satellites in it. Hmm.
0.9 probability each.
Okay, the probability
I'm asking.
of detecting
I'm asking you if that's 0.9 each.
each is that. This is each, yeah. So satellite 1, 0.9, that it's going to detect a missile coming in. Satellite 2, 0.9, okay? So is this an and kind of thing or an or kind of thing? That at least one. Let's go back in the notes. Hint. The probability of at least one is 1 minus the probability of none. Okay, so let's go fast forward past Ralph. So what do I need to know to answer this? Probability of none. Okay, so what's the probability that none detects?
Wait, would it be
It is. This one missed, this one didn't detect, and this one didn't detect, and this one didn't detect. 0.1 times itself 4 times. You're right. So 0.1 to the 4th power. That's only going to happen 1 in 10,000 times. Does that make sense? Okay. So then the probability at least one fails to detect. Wait. Oh, no, detects at least one is what? 1 minus this? And it says, would you feel safe with this system? Yeah. Pretty high chances of detecting. So tomorrow we're going to be talking about 5.4. If you want to look at it, it'll help you because it's the most confusing of these 4 sections. I'll leave it up to you. All right, thanks for the good thoughts today.